Hello and welcome to Diksha Karnataka YouTube channel, and in the one shot series I am going to discuss another super important chapter, that is electromagnetic induction. So we have covered all the chapter electrostatics, electric potential and capacitance, current, electricity, moving charges and magnetism and matter. Now it is electromagnetic induction. We are going chapter sequence wise. After this we will obviously cover alternating current and EM waves, then we will move towards ray optics and the remaining chapters. So electromagnetic wave is one of the most conceptually and what should I say, one of the most important chapter for your PUC preparation as well as KCET preparation. In PUC also you are going to get 2 MCQs, and in KCET also you are going to get 2 MCQs. The MCQs are generally easy, but you need to understand the depth of the concept in detail, so that you will not make a mistake that many students make. Okay. So basically we are going to discuss the entire chapter. Let's look into the chapter content. So we will basically introduce Faraday's law, Faraday's experiments. Okay, then we have concept of magnetic flux. We have done electric flux. Now what is the difference between electric flux and magnetic flux? We will see that also. Faraday's law of induction, Lenz law and conservation of energy. We will also discuss motional EMF, inductance, mutual and self. We will also discuss AC generator and summary, as well as 10 MCQs. So everything we will discuss in today's session. Right, remember that this is a very important session for all of you. So if you feel that our series, our channel is helping you with your PUC as well as your KCET preparation, don't forget to subscribe, because what we have seen that 80% of our viewers are actually coming and not subscribing to our channel. So please don't be like them, please do subscribe. Also another important message: if you think this video is good for you, then don't forget to give it a thumbs up. Right, we always thrive on getting your support. Without your support we are nothing. So always try to support us by clicking on this like button. Right, let's start. Okay, so we will start from Ørsted, move towards Faraday, and moving magnets produce current or not. That is my major question. Is we have seen that moving charges produce magnetic field, right? Moving charges produces magnetic field, and moving charges means what? Moving charges means current, right? So current can produce magnetic field. Now another important point is that the nature loves symmetry. What does that mean? If you see that any natural object, for example our earth, it is spherical. Sun, spherical. Spherical is the most symmetrical object in nature, right? Another thing is that if you watch any leaves of a plant, they are symmetrical from both sides, right? So nature loves symmetry. Everything in nature is basically symmetrical. So if current can produce magnetic field, then a magnetic field should also produce current. So that is our goal. That goal we will keep in our mind, and we will see whether we can achieve it or not. Okay, let's see. Okay, in early 90th century means 1800. Okay, 1800 to 1800 to 1899 is called 19th century. Sorry, my spelling mistake. 19th century means 1800 till 1899. From 1900 till 1999 is basically 20th century, and we are currently in 21st century. So that means almost 200 years back, early 19th century, Ørsted is a famous person. Okay, Ampere and others showed that Hans Christian Ørsted, but by the way, if you are thinking what is his name, okay, Ampere was somewhat a student of Ørsted at that point of time. Okay, showed that moving charges current produce magnetic fields, right? Moving charges or current can produce magnetic field, that we have studied in our previous chapter. Okay, a current deflects a compass needle placed near it, right? If you have a current carrying conductor, if you place a magnet near it, it gets deflected. Okay, if you point your finger, all the fingers in the direction of the current, then your thumb points the deflection of the north pole of the magnet. That's what we have learned, right, in our lower grades. Now, natural question, as I mentioned that nature loves symmetry. So, can moving magnets produce electric current? So, moving charges produce magnetic field. So, if we have a magnet, if we move it, can we produce electric current or not? So, that's how science progresses. So, you have to ask questions. So, this is the natural question that came to their head, and they are tried to solve this problem. Okay, Michael Faraday and Joseph Henry. So one is from England, one is from USA. At that point of time, there was no aeroplanes. If you want to travel, excuse me, between places, you need to have ships which take much longer time to reach from one place to another. You can realize that there is a problem happened in the Middle East, and our oil tankers are not coming because of the conflict, right? So that was the only communication, and it took a long time to travel from one country to another. Okay, so they were at separate countries at that point of time. Around 1830, okay, 1830, almost 200 years back, right? If you add 4 years from now, so it will be almost 196 years back. Okay, showed that currents are induced in closed coils placed in changing magnetic field. So if you are changing the magnetic field, it can produce electric current. These electric currents are called induced current. Not naturally, there is no current. Okay, naturally no current is there, but if you are changing the magnetic field associated with the coil, okay, then it basically inducing a current. We will see that, don't worry, we will see everything in detail, but the experimental background, the theoretical background is that the question that came into our mind, that can moving magnet produce electric field or current? Yes, it can produce current. Okay, so if you change the magnetic field lines associated with a closed loop is important. That this term, remember that closed loop, we have discussed it many times. Again, closed loop, if there is a closed loop, the current gets induced. Okay, so that phenomena is called electromagnetic induction. Electro is basically the electron or current, magnetic means the motion of the magnet, and induction is the process through which we are inducing electric current. Okay, the phenomenon in which electric current is generated by varying magnetic field. Phenomenon means the incident or the process. Okay, it's the language. The phenomenon in which electric current is generated by varying magnetic field is called electromagnetic induction, right? Remember that. Now, what is the use of this? Okay, so at that point of time, someone asked Faraday that we already have a current producing mechanism. Even though we do not know about exact nature of current, we actually had a way to produce current back then as well. Even though it was not there completely in India, but in many other countries, the current was already there. It was started to coming. Okay, not like lit up rooms like today, but yes, it was there at that point of time. Current was discovered, batteries was discovered. Okay, but someone asked Faraday, okay, magnets are there, currents are there, we should work on improving the current system rather than deciding this, what is this new thing. Okay, the Faraday's reply was epic. Remember that. What is the use of a newborn baby? Do we know what a newborn baby is going to be? Whether it will be, he will be a super duper scientist, or he will be just an ordinary person like us, or he will be a terrorist, or he will be a leader like our greatest prime minister. We do not know what he is going to do, right? So when someone is born, we will not be able to say that he is going to do something big in future. Okay, so that is not going to happen, right? So a newborn baby does not know what is going he will become in future, right? Similarly, their parents also do not know that what will be the use of it. So that is the question. So that is the scientific mindset that all of us should have. Okay, whenever you see something new, you should not discourage it. Similarly, you should not encourage it completely until you understand what is the use of it. You have to figure it out. Same thing can be used to build a nation and can be used to destroy a nation as well. So that is dependent on the user. Okay, so now let's see. Now, what are the uses in our life nowadays? So that was his answer in the past. Now if you see electric generators, the current that we receive in our home, alternating current, actually based on this principle, and it is basically modified from there. Obviously the basic principle is this: motion of magnet or magnetic field lines through a coil producing electric current. That's it. Okay, all that mechanism, all the complexities that we see in our day-to-day life is based on this very simple concept. Next, that is electrical generator. What else? Transformers. Okay, transformers is basically the way to transport electricity from a power station to our homes. Okay, if we send the same current through power station to our home, there will be huge cost. The electricity that we are producing, if we are sending the same current back to our homes, the cost of electricity should be very, very high. The bills, for example, in 1 month's electricity bill in Bangalore, if suppose it is 2500 rupees, okay, and if there was no transformer, the electric bill could be up to 2.5 lakhs. Okay, 2500 to 2.5 lakh rupees. So that is the difference. That amount of money is being saved by this simple device, transformers. Okay, transformers are used various places. There are different stages of the transformers as well, but that is a lifesaver. That saves a lot of money. You do not realize it. In future, maybe if you become an electrical engineer, you will realize it. Okay, now modern life, no lights, no trains, telephones or computers without this discovery. Okay, so basically this discovery helped us to build our modern society. That is the pioneer for our modern current society. Okay, without this we would have nothing, right? We would have been still in the ancient ages, right? So this is one of the major discovery by Faraday, and that baby is now grown into a well-established man. Okay, now experiment, that magnet and coil experiment. This is an important experiment that being asked in the exam from time to time. Let me just a second. I don't know what happened. Okay. I am not able to select the color for some reason. Anyway, let me use this color and combine this. Okay, so if you see that there is a coil through which current is being allowed, and we have a galvanometer. Okay, we have a coil and we have a galvanometer. This is the first experiment. Okay, we will improve on this experiment. This is the first experiment. This experiment is being asked in your exam many times. Okay, explain coil magnet experiment. So this is a coil. Coil means in one single turn is called one loop. If multiple turns are present, that is called coil. Okay, so there are multiple turns are present over here, and that is a example of a coil. Now through this coil there is a gap. You can take this magnet and you can move it towards the coil and back it, or you can take the magnet through it completely, whatever process it is. So you basically need to have a magnet, a coil and a galvanometer. What is the role of the galvanometer? When you push the magnet, if there is a current is being induced in this coil, that current can be detected by this galvanometer. It will not give you the exact value of the current, but yes, it will tell you that there is a current that is flowing in the galvanometer. Okay, you take the magnet, you take the coil, you push it, you will see that the galvanometer is getting deflected. That means a current is being induced in this coil. Okay, so north pole pushed towards the coil, so you have a north pole and it is being pushed towards the coil. Okay, galvanometer deflects, so as soon as the current is flowing, you see a deflection in the galvanometer needle. That means you are getting a current. Okay, in understand the steps, you have to write the same steps in the exam as well. So north pole pushed towards the coil, the galvanometer needle deflects. So that means what? We can infer that current is flowing in the coil. Okay, now if you take the magnet and keep it stationary, magnet is not moving. Okay, no deflection, that means no current. No deflection, that means no current. Next, magnet is pulled away from the coil. You are taking the magnet and you are pulling it away from the coil. That is also important. Deflection reverses the direction. That is super duper important point to remember. Deflection reverses the direction. So if when you are taking the magnet in this side, okay, suppose the galvanometer deflected on right hand side. Now when you are taking the magnet in the opposite side, now if you are taking it away, pulling it away, the galvanometer needle will deflect in the opposite side. Galvanometer by default always stays in the middle. Okay, galvanometer, that is the beauty of galvanometer, that's why we are using galvanometer. So galvanometer needle is always stays like in the middle. This is the 0. Okay, so if you are taking the magnet towards it, it deflects on the right hand side. Okay, so when you are taking the magnet towards the coil, it deflects on the right hand side. Okay, so that is the deflection. And if you are pulling it away from the coil, then it deflects in the other side. Okay, so deflection happens in the other side. Okay, so that is super duper important. This point you cannot miss. This point has to be written if the question is being asked that what happens when in coil magnet experiment. You have to mention that when the magnet is brought towards the coil, you get a current. When you are making the magnet in the opposite direction, the deflection reverses, the direction of deflection reverses, that gives a opposite current. Okay, so this is basically meaning the current is opposite. Current in opposite direction. In opposite direction. This is super duper important. So when you are moving the magnet away, the current is still flowing, but it is flowing in the opposite direction. Now instead of north pole, if you are moving the south pole, what happens? Deflection opposite to that of the north pole case. Faster motion, large deflection, larger current. So if you take the north pole, okay, if you take the south pole and move it, you get exactly opposite of whatever north pole is giving you. Suppose in case of suppose this is the north pole in moving towards, this is the this will be the south pole moving towards. This is north pole moving opposite direction. This will be south pole moving opposite direction. So basically the order reverses. That's it. Clear? If you have any doubts, mention in the chat section below. I will try to address them as much as possible. Okay, now if the motion is very fast, if you take the magnet very fast, okay, then what happens? The deflection increases. The deflection of the needle increases larger than the previous one, so that means the current is larger, the amount of current increases. Suppose when you are taking it slowly, say 1 ampere current is flowing, for example, if you do it faster, then deflection will be 2 ampere, so it will give you 2 ampere current, so current increases. Okay, coil moved, magnet fixed. Now magnet is fixed. If you move the coil, what happens? Same effects as observed. Okay, so if you will get the same effects as if the magnet is moving. So it does not change the effect if you just move the coil. Coil moves or magnet moves, as long as they are moving, you will get a current. Okay, now based on the direction, it can be forward and backward. Okay, in generally the the power stations, they can have moving coil as well as moving magnet generators. Okay, so moving magnet means the magnet is moving, moving coil means the coil is moving. So those kind of situation are there. Okay, now next, now if you replace the magnet with a coil, okay, if you replace the magnet with another coil, okay, bar magnet is replaced by a coil C2 connected with the battery, same thing. Okay, so if you see that we have a coil which is connected to the galvanometer, so this portion remains unchanged. Okay, and instead of bar magnet we have added another coil and it is connected to a battery. What will happen now? Now you are taking this coil towards and away from. We know that a current carrying loop or current carrying coil gives out its own magnetic field, right? On its axis we have calculated the equation. Now if you have another coil and if you allow to make this coil move and forward and backward, this also behaves like a magnet, right? We have seen that last chapter and last to last chapter as well. So when you are moving the coil towards and away from the primary coil, okay, what happens? You are going to get another deflection. Everything remains same. Okay, bar magnet replaced by coil C2. Steady current in C2 produces a steady magnetic field. When C2 is moved towards C1, the galvanometer deflects. Okay, moving C2 away, deflection reverses, relative motion again. So again, if you are moving the coil towards it, you get a deflection. You are taking it back, you are getting a deflection in the opposite direction as well. Okay, now no motion at all. So if you fix both coils, you are not moving them at all, both coils held fixed, C2 connected to the battery through a tapping key, K, press key, release key, iron rod inside the coil makes the deflection much larger. Okay, so momentary deflection in the opposite direction. So as soon as you switch on the circuit, suppose you have a key over here. Okay, you have a key over here. If you put on the key, as soon as you put on the key, there is a deflection, but then it stops. If you have a iron bar inside this system, okay, then also you get a very large deflection, but as soon as you stop the current or if you put the key and leave it, okay, you will get only a momentary deflection. You will not get permanent deflection. For permanent deflection, the motion needs to continue. For permanent deflection, the motion needs to continue. That is the very important point to remember. Okay, so now let us see what is the conclusion of this experiment. It is the relative motion between the magnet and the coil, more generally the change in magnetic field through the coil. Okay, we will see that what happened here is when you are, suppose we have a coil, and a galvanometer connected. Okay, so what happens when you have a magnet? Let us take the easy one first. You have a north pole, you have a south pole. So we know that magnetic field lines exit the north pole, okay, and it comes back through this to the south pole somewhere, sometime. Okay, it comes back. Does not matter, but it exits the north pole, right? Some fields like that. So it always comes back to the south pole from somewhere, okay, somehow. That we are not interested here. We only want to see that the number of field lines, if you take it forward and backward, what happens? The number of field lines crossing this coil changes. Number of field line changes. Sometimes it can be 3, sometimes it can be 5. Sometimes it can be 30. So based on the number of lines and the magnet design, so number of field lines passing through this coil changes with the motion of the magnet. So changing magnetic field produces current. So changing magnetic field produces electric current. Right? This is called electromagnetic induction. So magnetic field through the coil changes, magnetic flux through the coil changes, okay, EMF induced in the coil, current flows. So this is the process. Okay, we will see what is magnetic flux. We have not seen that, but magnetic field, changing magnetic field gives rise to changing magnetic flux, and that gives rise to electromotive force. Electromotive force is same as a battery, so that changing magnetic field acts as a battery, right? Interesting, right? So the changing magnetic field acts as a battery, and that gives rise to current. Clear? Any doubts? Mention in the comment below. Now we will see what is this term magnetic flux. So far we are discussing magnetic flux, magnetic flux, magnetic flux. Let's see what it is. Okay, so magnetic flux, if you remember in electricity, current electricity, we have a surface through which some electric field lines are passing through this, right? And we said that we need to find the angle of the electric field, we need to find the angle of the surface, and then we said that it is basically E dot A, that we called electric flux. Now the same thing we can apply for magnetic flux as well, and because normal phi is used for electric field, we will use phi B for magnetic flux. Okay, the formula is same, only thing is instead of electric field we will be use magnetic field. Okay, so B dot A equals to BA cos theta, that term is called magnetic flux. So basically it is the number of field lines that is passing across a surface in the normal direction. Now normal direction is not always there, so you have to use the cos theta as a component. Okay, theta is the angle between magnetic field B and area vector A. Okay, this is the angle between B and area vector A. Okay, magnetic flux is a scalar quantity. As you can see here, it's a dot product. Dot product refers to a scalar quantity. Okay, SI unit is Weber, Tesla, meter square. Its SI unit is Weber or Tesla meter square. This is also a super duper important question. Okay, sometimes they will say that what is the unit of magnetic flux? Magnetic flux, what is the unit? Okay, option will be Weber meter square, Tesla per meter square, Weber, okay, or Tesla meter. You need to identify it is either Weber or Tesla meter square. It is not Tesla per meter square, it is not Weber meter square, it is Tesla per meter square. Tesla is the unit of magnetic field, right? If you forget, Tesla is the unit of magnetic field. If you multiply area with that, you get the unit of magnetic flux. Okay, for a non-uniform field, if the magnetic field is not uniform, it is varying from point to point, then how can you calculate magnetic flux? For individual point, you need to find these quantities, okay, and then you have to add them separately. For individual points, you need to add find the magnetic flux. This is the individual point magnetic flux, and then you need to add them to get the total complete flux. Now this is for a surface only. Now as in the previous chapter we have learned that magnetic flux is basically for a closed surface, magnetic flux is 0. If the surface is closed, the field lines, whatever is coming from this side has to exit the magnet, and if the magnet is itself is inside, then field lines will always be closed and it will be 0. So magnetic flux for a closed surface is 0, but for an open surface it is not 0. Students often relate to that fact that okay, for closed surface magnetic flux is 0, so magnetic flux is always 0. No, magnetic flux is not 0 if the surface is not closed. For closed surface magnetic flux is 0. For closed surface magnetic flux is 0. For open surface, however, magnetic flux is not 0. Okay, magnetic flux for open surface is not 0. Open means normal surface, okay? So it is not closed. If you close it from all sides, then it is called close. Okay, if it is a like that, like a piece of paper, it is a open surface. But if you fold it to make it a sphere or a say pyramid, then it's a closed surface. Okay, remember that. Special cases for phi. So if phi equals to 0, then phi magnetic flux becomes B into A. Okay, field perpendicular to the plane, parallel to the normal, maximum flux. If theta equals to 90 degrees, phi becomes 0. So this is the surface, this is the normal, this is the magnetic field. In that case, so this is the first case where this is the surface, this is the normal. Okay, this is the magnetic field. They are parallel. That means the flux is maximum. Okay, here the angle is 90 degree, flux is minimum, and here this is the surface, this is the normal vector. Okay, and this is the magnetic field. In that case, it will be minus BA. Okay, field anti-parallel to the normal, maximum magnitude is negative in sign. Okay, now 3 ways that you can change magnetic flux. Magnetic flux, as you have realized, that changing magnetic flux is super duper important. If you can change the magnetic flux linked with the coil, okay, you can induce electric current, which is important. Electric current is our day-to-day requirement. So how can we change the magnetic flux linked with the coil? So the way to change magnetic flux is basically you can change the magnet itself. Okay, so move the magnet or change the current in nearby coil. Okay, in the previous experiments you can vary the current, okay, or you can move the magnet. If you move the magnet, then the magnetic field changes forward and backward. If you move the magnet closer to the coil, more magnetic field; away from the coil, less magnetic field. Changing is important. Okay, change is only constant. So that's what it means, right? So if you change the magnetic field, then flux changes, right? Phi is equal to B dot A, B changes, flux changes, current is induced. Change area. If you can dynamically change the area, okay, stretch, shrink, or slide apart of the loop, the field, this is called motional EMF. This is slightly tricky to achieve. If you change the so for example, we will do that derivation. We are sliding a rail along a path. Okay, so that is also possible to induce current, but that is very tricky. Generally we do not do that, but it is also possible. Okay, change theta. So this is the easiest one, that you rotate the coil in the magnetic field. Magnet is fixed, you are rotating the coil, or the coil is fixed, you are rotating the magnet. The theta between the normal and the magnetic field changes, and that gives you induced EMF. This is the way that our electric generators work. Okay, electric generators that generate electricity and sends the current to our home. That is the main principle behind it. Okay, we have something you may have heard about, turbines. Turbines, so some water is flowing through a turbine. Okay, turbine rotates and we get electricity. You may have seen the wind turbines. Okay, there are long fan kind of thing, right? So it rotates with the wind and it produces electricity. Basically the rotation of the fan produces rotation of the turbine present inside that big machine. Okay, and because of the rotation of the turbine is basically linked with the coil or with the magnet. Okay, turbine is basically a rotatory fan which is linked with the coil, and that coil is rotating in a fixed magnetic field, and that is producing the required EMF, right, for the current to produce. Current produced like this. Okay, any changes in B, A or theta, basically phi B changes and EMF is induced. Okay, phi is equal to, always again once more, phi B is equal to BA cos phi, cos theta, right? So if you change the theta, you change A or you change B. These are the 3 ways to change the induced EMF. Okay, now Faraday's law. Now we are going to discuss the most important thing, that is Faraday's law. So we have basically seen current is produced when you are moving a magnet or you are moving a coil, okay, or you moving a current carrying coil, and that is being induced in the coil. Now, there is the induced EMF. Now this induced EMF basically obeys certain laws. So that law is Faraday's law. First law is Faraday's law. So obviously anything happens in nature has to have certain amount of law present in it. So the first law is Faraday's law. Okay, what is this? The magnitude of the induced EMF in a circuit is equal to the time rate of change of magnetic flux through the circuit. Okay, so basically the induced EMF not only depend on the change in flux, but it depends on the time rate or rate of change of magnetic flux. That is important, because if you are doing it faster or slower, that is also important. You just doing it is not important. So if you are solving 60 questions in KCET exam, it is important, but you have to do it within that given 60 minutes only. So that is time rate of solving questions should be one question 1 minute. So that's what the Faraday is trying to tell you, right? Jokes apart. So basically the rate of change of magnetic flux linked with the coil is important. So according to Faraday, the induced EMF, whenever we say current, before talking about current, we need to talk about EMF. Basically EMF gives you the current. Okay, so based on resistance you get current. So EMF is more important, more fundamental than the current, because current can vary based on the resistance. Okay, if the less resistance you get high current, high resistance you get less current. So that is not a parameter. The parameter is here the induced EMF. Okay, that is the voltage, okay, that is producing. It is given by minus d phi b by dt. Okay, minus d phi b by dt. D phi b is the change in flux and dt is the change in time. So d phi b dt gives you the induced EMF. Okay, now if the coil, instead of having one turn, this is for one turn only. This is for one turn. If the coil, instead of having one turn, if it has multiple turns, say example n number of turns, then the induced EMF becomes minus n d phi b by dt. So you have to multiply by n. Same process that we have followed in the previous cases, that one coil, single, n number of coils, you need to multiply with the n. Same thing you need to do it over here as well. Okay, so negative sign gives the direction. We will talk about the negative sign in next part. Okay, when next part means not part 2 of this video. This is a one shot video. Next part means next topic. Okay, where Lenz law coming. Okay, for a closely wound coil of n turns, each turn contributes to the same EMF. So the total EMF is n times the single coil. Okay, so if the one turn is there, whatever EMF is produced, if you increase the number of turns, each turn is actually contributing equal amount of EMF, and that's how the EMF increases. That's how we produce, even though with a small limited magnet, limited power, we can produce high amount of current, because we can increase the number of turns. More number of turns produces more EMF. Okay, so induced current I is equal to epsilon by R, where circuit is closed with resistance R. So current is basically given by induced EMF divided by R. Now that is also important point to note, that when we are solving a question, there was a time that they have given some value from where you can calculate EMF. Okay, but they are asking you what is the current. So remember that current, to calculate current, you need to first calculate the EMF. Second, you take the resistance and divide the EMF with the resistance to calculate the final current. Right? That is super duper important. Now let's see one solved question. Okay, a square loop of side 10 centimeter and resistance 0.5 ohm is placed vertically in the east-west plane. A uniform field of 0.1 Tesla is set up across the plane in the northeast direction. So the plane is east-west direction. East-west direction, if you are someone who do not are not comfortable with direction, remember this is your north, this is your south, okay, this is your east, and this is your west. Okay, north east direction. So northeast direction is this direction. This is northeast. Okay, this is the direction of the plane. Sorry, the plane vertically in the east-west direction. The plane is vertically east-west direction. So plane is placed like this. This is the plane's vertical direction. So the normal to the plane is in the north direction. Normal to the plane is in the north direction. So northeast direction is the magnetic field. This is the direction of the magnetic field. So what is the angle between the normal vector? Say this is the normal unit vector. What is the angle between normal vector and this? This is 45 degrees. The angle here is 45 degrees. Okay, northeast always makes an angle 45 degree with north as well as east. Okay, northeast always makes an angle 45 degrees with the north as well as east. Okay, so the angle between the surface and the magnetic field is 45 degrees. Now what else is given in this question? That the magnetic field decreased to 0 in 0.70 second. 0.7 seconds. Initial value was 0.10 Tesla. So magnetic field changes from 0.10 Tesla to 0 in how much time? In 0.7 seconds. Okay, now you have to basically, you cannot just divide it and you cannot find the induced EMF. What you need to do is first find the flux. So what was the initial flux? Initial flux, say phi B1 is given by BA cos 45 degrees. Okay, northeast always makes an angle 45 degree with the north, same with the east as well. Just remember it. Okay, so BA is given by BA. Now here it is a square loop, 10 centimeter per side. So square loop is square, right? Each side has 10 centimeter. So what is the area of this loop? The area of this loop is given by 10 semi into 10 centimeter, right? So that is 10 into 10 to the power of minus 2 into 10 into 10 to the power of minus 2, that is 10 to the power of minus 2 meter square. Just simplify it, you will get. Okay, this 10 to the power plus 1, 10 to the power plus 1, one of the 10 to the power of minus 2 will cancel, and the ultimate area is 10 to the power of minus 2 meter square. Now let's put the value. So initially the magnetic field was 0.1, area was 0.2, and cos 45 is 1 by root 2. Cos 45 is 1 by root 2. So the initial magnetic field is 10 to the power of minus 3 divided by root 2. 0.1 can be written as 10 to the power of minus 1. So phi B1 is calculated. What is phi B2? Final flux. So magnetic field is becoming 0. So if you put 0, final flux will become 0. Right? What is the induced EMF? Induced EMF is given by minus final flux minus initial flux divided by the time, change in time. Okay, so change in time is given here 0.7 second. So that's what you need to use here. So it will come out to be minus 10 to the power of minus 3 by root 2 into 0.7. Okay, and if you simplify it, you will get the value to be around 1 millivolt. It will be approximately 1 millivolt. Okay, you will get the value around 1 millivolt, and then you need to calculate the current. That is super important. This is not done. You also need to find the current as well. The current will turn out to be 2 milliampere. If you solve the current, now how to find the current? Here if you see that resistance is given 0.5 ohm. So once you calculate the EMF, you just need to divide the current, divide the resistance, you get the EMF. You divide the EMF with the resistance to get the current. So the current here will be 2 into 10 to the power of minus 3 or 2 milliampere. This obviously you require a calculator. This is a PU level question, not a KCET level question. In KCET, if the same question comes, the calculation part will be slightly easier. There should be some values given where this 2 will be cancelled. You don't need to use a calculator to find these values. Okay, this is a PU level question, so can be asked as a 3-marker objective question, or not objective, a 3-marker short answer type question. Okay, now let us think something like an experiment. Okay, so you are an experimentalist and you are planning to do an experiment on this electromagnetic induction, and your target is this: how to get a larger deflection. So you are getting a current, how can you get a larger deflection in the galvanometer? The same experiment that we are talking about. Put a soft iron rod inside the coil C2. Okay, if you put a soft iron rod, okay, that increases the magnetic field produced, and that actually gives you more magnetic field linked with the coil, and that's how you get a more induced EMF as well. C2 means, what is C1, C2? The experiment that we have performed, the original coil, which is OG coil, which is fixed with the galvanometer, this is my C1. Okay, and when you are adding it to another coil, this is C2. This is C2. Okay, so if you add an iron rod over here, the more magnetic field increases. Okay, magnetic field, we know that inside a coil is B is equal to mu naught Ni when there is only air. So if you put a soft iron which has a very high mu, you get mu Ni. So the magnetic field produced by this solenoid or this coil increases, and that actually gives stronger response with the deflection. Okay, connect the coil to a more powerful battery, that is, you increase the voltage of this battery. If you increase the voltage of this battery, you get higher deflection. Secondly, move the arrangement rapidly towards C1. So if you are moving this very fast, super duper fast, then also the deflection increases. Use more turns in C1. So basically, if you increase the number of turns over here, then also the induced EMF increases. That gives you larger deflection. Larger deflection is what? Larger deflection means higher EMF, higher current. So that's what we want to achieve, right? If it is in the order of milliampere, we are not super satisfied. We want in the order of volts, 220 volts to be precise, right? And for 220 volt, we need a very high amount of current as well. So that's what our target is, and to achieve that, what we will do, we will implement one of such things. Okay, and also try to keep the configuration as close as possible. Okay, in many cases what happens is that we use a configuration like this. So this is one coil, this is another coil. Okay, there is a iron fixed like this, so the distance between them is very small. Now how do we change it? We change it by changing the resistance of the circuit. We change the current by changing the resistance of the circuit, and that's how the linked EMF changes. Okay, this is the advanced technology. We will learn about it in mutual induction part briefly. Okay, so this is how you can increase the current or increase the induced EMF. Okay, no galvanometer, no problem. Now if you remove the galvanometer, what happens? Replace the galvanometer by a small torch bulb. Okay, if you replace the galvanometer with a small torch bulb. Now torch bulb, many of you may not have seen it. Okay, it is almost not super common nowadays. When we were kids, there used to be load shedding which was going on because we are consuming much more power during the summer days. So the government used to turn off all the power towards our homes to conserve some power. Okay, so that was called load shedding. Okay, load, there are too much load, it was shedding. right? Nowadays also it is happening, but not as a load shedding, but and the streets were not well lit up, so you used to have a torch to find our way. Okay, I had a small torch. I used to go to tuitions using that torch, okay, when I was a kid. So now many of you may not have seen that torch bulb, but in some laboratories and experiments some of you may have seen it. So that torch bulb, if you replace the galvanometer using a torch bulb, what happens is that then if you do the motion, the torch bulb will glow. The torch bulb will glow. Relative motion between the coils makes the bulb glow. Proof of induced current. So you are actually moving magnet, and that helps us to glow a bulb. Isn't that beautiful? Right? So that glow signifies that there is electric current that is produced in that circuit. Okay, Faraday, one of the best experimentalists ever, was legendary for such innovation. So obviously Faraday is one of the greatest experimentalists. There are some people who are theorists, some of them are experimentalists. Okay, Newton was somewhat balanced between theory and experiments. Okay, mostly he was a he was into theory. Albert Einstein, however, he was theoretical physicist. Okay, he did lot of theories about lot of things. Okay, he hardly did any proper experiments for his experiment. He did lot of thought experiment. Okay, so that's the difference. Whether Faraday was someone who did a lot of experiment by hand. He learned a lot of things by doing things. Okay, so in physics, it is not only important to give us a theory, but also doing experiment as well. So that's why one important point here, just to off topic, little bit of off topic, that when a person gets Nobel Prize in physics, okay, if you just give a theory, you are not selected. If you just do some experiment, you are not selected. If the theory and experiment both are done on a topic, then only you are going to get a Nobel Prize. Now, many cases what happens, a person A gives a theory, a person B does its experiment, and both persons together get their Nobel Prize. Okay, that's how it happens. Okay, even though Albert Einstein got Nobel Prize for photoelectric effect, he actually did not perform the experiment. He only get the theory, which is obviously correct, and that's why he got the Nobel Prize. So there are a lot of things which people do. Some people only do experiments, some people only do theory. Based on that, we get a lot of interesting results. There are some cases the experimentalists themselves find the theory and give it, so they get the Nobel for their achievement as well. Okay, so that is interesting, right? So if you want to get a Nobel Prize in physics, you know what you have to do. You have to either find a theory which has no experimental proof, prove it that okay, this is a very interesting theory. It has to be something world changing, something like that, which is completely different. Okay, some important theory which never had any experimental proof, prove them, then you will get a Nobel Prize. Okay, or if there is something which is already experimentally established but no one knows why it is happening, then if you can develop a theory for that, which is most common, most people, those who are trying, the number of competition is here is very high, because performing experiment is difficult, but trying to figure out a theory may be easy, because you can figure out 1000 different possible theories, maybe one of them is correct. Okay, so that is one important point. So 1000 people are working for some experiments which are being done on their theories. Okay, but performing experiments on some theory is very, very less. So try to do that and you will get a Nobel Prize next. Right? Now, next is Lenz law. So Lenz law is basically talking about the conservation principle. We know that energy is always conserved, right? So that's what Lenz law talks about. So Faraday's law says that if there is a change in flux, that will give rise to current. That's it. He does not talk about the conservation of energy. So Lenz is a theoretical physicist. Okay, he came up with a problem of himself. Okay, so what if I have a coil? Okay, imagine I have a coil. Okay, I have a coil fixed with a galvanometer, and I have a magnet. It was his thought experiment. Okay. Now, when I am pushing the magnet towards it, there will be some induced current produced in this coil, right? If you push this magnet towards it, there will be some induced current, right? Now, what if when we are pushing this, there is a current flowing through the coil? So current flowing through the coil will now have a magnetic field of itself as well, right? Current produces magnetism, so magnetism is producing current, current is producing magnetism, right? So now what will happen? What will be the effect of this magnetic field on its source, on its parent? Okay, suppose you are pushing this north south towards this coil. Suppose this side becomes south. Imagine this side becomes south, this side becomes north, right? This is a current carrying coil, so it behaves like a magnet. Now what happens is that you push the magnet towards this for some time. Okay, you push the magnet towards it for some time, then this north and this south, they will start attracting to each other, right? You don't need to do anything after that. You push it, as soon as south pole develops, the south pole is now inviting this north pole towards it, the north pole comes towards it, and then it goes back and the pole reverses. So it's basically doing to and fro motion without any extra energy required. We are getting energy. So it's like getting an infinite energy without spending anything. So you are getting chocolates at your home every day, hundreds of chocolates without paying anything. Would that be great, right? Maybe not chocolate, maybe free fire credits, right? So you are not doing anything, you are not paying anything, you are getting a lot of stuffs at your home. That would be great, right? But in practicality, that is not possible, right? If you want to get something, you have to pay for it. Same goes with nature as well. If you want to get energy, you have to spend energy. So this is called a perpetual machine. Perpetual machine means you do work once and then for eternity you are going to get current. If that would have been happening, then our electricity bills would have been, say, 1 rupee per month. Only the maintaining the line, etc. Current would be free. Okay, even we can fix some machine in our home and it will produce electricity for us for free. Okay, we do not need to pay any electric bills, right? Wouldn't that be amazing? Obviously that is not happening. We are paying electric bill neither 2.5 lakhs nor 2500. We are paying something like so that means this is not correct. So what is happening over here? So instead of south pole, there must be a north pole which will produce over here. This north pole, what it will do, it will not attract this north pole, but it will repel it. So if you try to bring this north pole very fast towards this coil, immediately another north pole will be produced over here and he will start pushing the magnet. So that's why you have to do an extra work to move towards this coil. That extra work is converted into electrical energy. So basically you are converting mechanical energy into electrical energy. Conversion of energy is happening. So that is conservation of energy. That is consistent with our principles, right? We cannot create energy out of nothing. So that's valid here. So this is basically, this is Lenz law. So Lenz law is basically talking about that thing. Okay, you cannot create energy out of nothing. Okay, so now the polarity of the induced EMF is such that it tends to produce a current which opposes the change in the magnetic flux that produces it. Okay, so the polarity of the induced EMF is such that it tends to produce a current which opposes the change in magnetic flux produced in it. So that is what is important. So if you are moving the north pole towards the coil, there will be a north pole on this side, south pole on the other side. If you take the same magnet and put the north pole away from it, then there will be a south pole which will try to stop the north pole, okay, and the north pole on the opposite side. So if you try to get too close, you will say don't come close, don't come close. But if you are trying to get away from it, then you say don't go, don't go. So it is like the you when you are a kid, okay? So your parents coming towards you and saying, hey, study, study. No, 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 I will not study, I will not study. When they are saying that, hey, don't go play. No, no, I will go play. So whatever they are saying, you are doing opposite. Same thing is happening here as well. So when you are bringing the North Pole, there will be a North Pole created which will repel it. If you are trying to take it away from the coil, okay, there will be a South Pole. There will North Pole and South Pole now attract each other and say that don't go far away, I am there. Okay, so that's what is the Lenz law talks about. So Lenz law says that flux increases induced current anti-clockwise. Okay, now if you forget how to find the direction of magnetic field, the same concept applicable here as well. So current must be in this direction, anti-clockwise direction. Seen from the magnet, coil phase becomes North Pole and repels the magnet. So this North Pole repels the magnet. Now when the magnet is moving away from, we get a clockwise current. Okay, we get a clockwise current. The clockwise current, what does it do? It creates a South Pole near the magnet and it attracts the magnet and asks him don't go. Okay, flux decreases, induced current clockwise, seen from the magnet, coil phase becomes south, attracts the magnet. So when it is trying to get close, it says North Pole. When it is trying to go away, it says South Pole. Okay. Now, as I mentioned, suppose the opposite were true. What would have happened? The coil phase would attract the approaching magnet. The magnet would speed up with ever increasing acceleration. Kinetic energy would grow without any work being done. So a perpetual motion machine, that is impossible. Perpetual means for infinite time. You do it once and it works for lifetime. That is called a perpetual machine. It's a hypothetical machine which is not possible in reality. Okay, perpetual machine means the machine where you do work once, small amount of work, then the machine starts producing work on its own. Okay, it's like a movie, science fiction. Okay, now what actually happens, that is important. The magnet experiences a repulsive force as you are trying to take it towards the coil. Okay, a person must do work to keep moving the magnet. Okay, this work appears as joules heating IR square due to the induced current. Energy is conserved. The minus sign is Faraday's law actually denoted this. Okay, so the negative sign in Faraday's law, where we say that induced EMF is minus n d phi by dt, d phi by dt. Okay, this negative sign indicates that the induced EMF opposes the cause which is producing it. Okay, so this actually gives you the energy conservation. Right, now one important point here, in reality when Faraday gave his law, he never said that epsilon is equal to minus n d phi by dt. He said that the induced EMF is proportional to n d phi by dt. That was his point. He said that induced EMF is proportional to n d phi by dt. Then people realize that it is actually equal. The proportionality constant is 1. Also, people realize that then Lenz law came into picture. Lenz gave his law that saying that, okay, if you are trying to bring it, it should be such a way, it should have been such a way that it opposes the cause. That means the negative sign was introduced. Okay, so Faraday says this one. Original Faraday's equation never had this negative sign. The negative sign comes from Lenz law itself. Okay, so that's how the Faraday's law and Lenz law sometimes is called first law of electromagnetic induction, second law of electromagnetic induction. Okay, nowadays it is called Faraday's law and Lenz law directly. There is no other name involved. So this negative sign in the Faraday's law actually encodes this. Encodes means it is embedded in the formula itself. You don't need to worry too much about. Okay, now some conceptual checks. A closed loop is held stationary in a very strong steady field. The current induced is. So here the loop is not moving. So induced EMF will be 0. These are the point of some questions. You need to check the answers. Okay, just remember the answers, because there will be a question where these points will be given as different options. So remember that if the loop is stationary, no current is induced. No current is induced. Only by changing magnetic flux you will get induced induced EMF. Now next, a rectangular loop and circular loop move out of the field at the same speed, the same EMF. The EMF will be same. A circular loop and a rectangular loop. Okay, rectangular loop EMF is constant. Circular loop rate of change of area varies, so EMF also varies. Okay, so if you take a rectangular loop, if the field is uniform, okay, the B into A is constant. But if you are taking a circular loop, okay, the rate of change can vary based on the orientation and design. Okay, based on that you will get a different EMF possible. Okay, a loop is placed in a changing electric field. Is current reduced? No, induced current needs to be changing magnetic flux, not a changing electric flux. So if you change, if you are basically placed in an electric field loop, there will be no induced EMF. Changing electric field will not produce any induced EMF. Okay, this is also super important. The changing electric field will not produce any induced current. Okay, changing electric field may produce magnetic field, but that magnetic field will be constant. So constant magnetic field, there will be no induced EMF. So that is the logic. Understand this. Two magnets approach an open loop with the capacitor, polarity of the plates. So determined by Lenz law, an EMF is induced even across an open circuit. Okay, so remember that if the circuit is open also, open circuit means we have a capacitor. Okay, obviously capacitor is not charged, so this is not part of the circuit. So if you move a magnet towards it, will there be any induced EMF? Induced EMF will be there, current will not be there. Okay, now based on the polarity and how you are trying to do it, there may be positive or negative, but yes, there will be induced EMF. Okay, there will be induced EMF. Okay, that is one very important point. It is not necessarily to be a closed circuit. Okay, now next we are going to do is concept number 4, which is motional EMF. What is motional EMF? Motional EMF is when you are moving in a magnetic field is static, you are moving inside a magnetic field, and what amount of EMF will be produced in it. So there is a small derivation in here which is very common, which will come in 3 marks every year. So let's start. Okay, now let us discuss about motional EMF. So what is motional EMF? So EMF from a conductor moving through a magnetic field. So if a conductor moves inside a magnetic field, there will be an EMF generated. Yes, we have seen that in a coil, you are moving a magnet, you have a current carrying coil that is moving as well, but here it is a normal conductor, not a coil or anything like that. A normal conductor moving in a external magnetic field, it will also induce a EMF, and that will can also give rise to current as well. So let's see. So here we have a rectangular railway line. Okay, a rectangular railway line, sorry. So this is the line. As you can see, this is the line. Okay, and this is the train. Okay, imagine this is the train, this PQ arm is the train, and it is moving in this direction with a velocity v. Okay, now we want to find how much EMF is generated across this. One side will be positive, one side will be negative. We can find the polarity later on, but for now just try to find out what is the EMF generated across this P and Q arm. Okay, so how to do that? First step, obviously, to apply the law of this derivation is important, by the way. Okay, first step is to apply the Faraday's law. Faraday's law says that the induced EMF is always minus d phi by dt. Here it is only one wire, so we are not using any n over here, right? If it is a coil or something, number of turns is n, then we use n. There is no n, so you just add d phi by dt. Okay, now what is phi? Phi is magnetic flux, which is given by, say, let me write d phi b. Okay, because phi generally for electric flux we use normal phi, for magnetic field we use phi b. So phi b, what is phi b? Phi b is magnetic field into area. Okay, now if you see that, what is this area? So this distance at some time t is x. Okay, the distance at some time t is given by x. Suppose the length of this wire which is falling inside this is given by, say, L. Okay, now what is the area? Area is given by b, length into breadth, right? That is L into x. Okay, this was x and this was L. So what is this area? The area must be length into breadth, that is L into x. Right, now let us try to find out what is the induced EMF. So induced EMF phi equals to minus d dt of BLX. Now if you see that magnetic field B is constant, is given, it is an external field, it is not changing with time. The length L is also fixed. The rail is moving in this side, so this length is fixed. Only thing that is changing is this x. Only thing that is changing is this x. So as the rod is slowly coming here from, suppose it came here, so at this position obviously the x value reduced, right? So only the value that is changing is this x. Remaining quantities are constant. So any constant in differentiation, they must come out of the differentiation. So it will be BL into dx by dt. Now what is dx by dt? Rate of change of x. Rate of change of x. So how x is changing? It is changing based on this velocity. X is changing based on this velocity. So that means we can say that dx dt must be equals to velocity. Now as if you see that velocity is in this direction, and with time, as time increases, the x value is decreasing. The x value is decreasing. As the time increases, the x value is decreasing. That means dx dt should be equals to negative of v. Dx dt should be negative of v. This represents that as time is increasing, x value decreasing, so negative of velocity v. So if you put that, you will get minus bl minus v, that is bvl. This is the induced EMF in a moving conductor. This is also called motional EMF. This derivation is super important, 3 marker. Almost every year it comes. Last year there was no derivation, so they gave write down the expression for motional EMF and explain the terms. So only thing you need to write is phi equals to epsilon equals to BVL, and then you write B is magnetic field, V is velocity of the conductor, L is the length of the conductor. That's it, you will get the full marks. Right, so this question is coming almost every year. Now do not ignore this negative sign. Many teachers, many textbook, they do not consider this negative sign. They just say that epsilon is equal to d phi by dt, then just write it down and then say x equals to dx dt is equal to v, which is wrong. Okay, the negative sign is there by Lenz law. You cannot avoid that. You cannot ignore Lenz law. So the negative sign should be there, but negative sign should be removed by this v. Okay, and this expression is the expression for motional EMF in a conductor. This is the conductor. Okay, now you can find the induced EMF as well. So induced EMF in this conductor such a way that it should oppose the original magnetic field. So suppose after induction, what will happen in this conductor? Obviously some current will be flowing, right? Some current will be flowing. So some current, assuming that there is a current in this direction. So what is the magnetic field due to this? Magnetic field due to this should be out of the page. Here the magnetic field given here is into the page, right? The magnetic field is given in this case is into the page, okay, and the magnetic field due to the conductor should be out of the page, so that they repel each other, they act against each other. That means this side should be positive, this side should be negative, because current always flows from positive to negative. So you point your fingers in the direction of the current, you curve your hand, you will get the direction of magnetic field. If suppose you want to find the magnetic field here, because this is the, remember, the area which is responsible for producing induced magnetic field is the inner part, okay. This field, outside field, does not play any effect. That's why we are only considering this part, okay. Anything outside, suppose the this is extended in this side, then they have no effect on induced EMF. Induced EMF is only because of the region which is enclosed by this loop, with this rectangular loop. Clear? Now that's why you can find the polarity. Now how to find the polarity? In case some random question is given, you need to check that what is the given magnetic field. Given magnetic field is into the page of the paper. Given magnetic field is into the page of the paper, so your induced EMF should be out of the paper. So you start with your fingers, these fingers, curl it, this will be out of the fingers, then you point your thumb, so this must be the direction of current, then only we will get the magnetic field which is out of the paper. So out of the paper means this, that means the positive side should be here, negative side should be here. So this is like a battery, okay, you can replace it with a battery with positive and negative like this. So current will be flowing in this direction. Okay, there was once one question in your model question paper, you can do and check that out if you want. Okay, now next is force on the charge in the rod. So charge Q in the rod moves in the speed V in the field B. Lorentz force magnitude is QVB directed along the rod towards Q. Work done moving from P to Q is QVBL. EMF work per unit done, it is given by BBL. This is another derivation, you can do that way also. Now stationary conductor changing B. So this is another way. Now you have a stationary conductor is stationary, but the magnetic field is changing. Can it induce EMF? Yes, it can also induce EMF, okay, and that can also be done. The time varying magnetic field can also induce EMF in a stationary conductor, okay. Electricity and magnetism are truly related, that can also be proven from this. Now here we have EMS across a rotating rod. So this is very interesting question. We have a rod, okay, which is rotating. This arrow is slightly off, the arrow will be here, okay. Some rod is rotating with a angular frequency omega, okay. A rod is rotating with an angular frequency omega in a magnetic field. We have some magnetic field, assume some magnetic field is there, and the rod is rotating inside this magnetic field. We want to find the induced EMF between this point and this point, okay. How to do that? So this can be asked as a cycle spoke is rotating in a magnetic field, or a clock arm rotating in a magnetic field, okay. What will be the induced EMF in that case? So what you should do, you need to consider this small EMF developed here is BVL, okay. Here it will be B omega R dr. Instead of V you have to use angular speed omega, and if you find the integration, the EMF will be half B omega L square. So half B omega L square is the induced EMF in a circular rotating rod. This, based on this, we have seen many questions coming from this chapter, be it PU, be it KCET as well. Derivation is not important, that's why I'm not doing the derivation, okay. You need to take a small portion dr and say that B to this dr, magnetic field is almost constant, and then you have to B omega R dr. What is omega R, by the way? V is equal to R omega. So velocity, you need to, instead of velocity, you need to put it like this, and then you have to basically integrate it throughout the rod, okay. That's how you can calculate now distance, obviously the angular velocity of each and every point is different. Okay, the major problem here is that as you are changing the r, okay, if you change the r, the value of velocity is different at each and every point. Okay, so based on that you need to consider the this equation. That's why it is not a constant. You have to first write in terms of small value, then integrate it to get half b omega L square. Okay, there is one small example. The values of BL omega are given. You are being asked to find the induced EMF, which will come out to be 157 volt. This is from your textbook, by the way. Now another important concept here is inductance. Okay, inductance basically determines how much flux will be linked with a given circuit. Okay, that's it. Okay, so let's see. Current can be induced in a coil by flux change from another coil. That is called mutual inductance. So basically we have, I can help you in the exam. If you show me some questions, I will show you some questions. Okay, so that is called mutual. So mutual understanding. So you have some of your friends who is helping you, and you are asking him in return to help you with something else. For example, you are writing physics exam, you don't know anything about physics. So you are asking your friend, you help me in physics, I am very strong in mathematics, I will help you in mathematics exam. Okay, so that is called mutual, right? Just for fun. Okay, that is mutual. So mutual means when changing in one affects the other. Okay, changing in one affects the other. Suppose we have a coil here, say a coil P through which some current is passing. Okay, this is the this has a battery or some source attached to it. Okay, some source. I am using a simple battery. Some current is flowing here. Okay, and we have a second coil. Okay, which is named by S. So these are the two brothers, P and S. P is basically having an own current, and he is asking S. So basically two brothers, one brother earned for the family, other brother is saying that okay, I have a business, why not you join my business, come and join my business. I will give you some funding, I will give you help, everything is required. So basically this current is asking the other current, other circuit, that I have a current, why you don't have, you should also have a current. Because of this, if some current is produced here, okay, then that is called mutual inductance. This is the property by which this is happening, is called mutual inductance. So one coil is helping another coil, which is normal, right? So now if it is from the same coil, then it is called self-inductance. Now how it can be a same coil? Okay, we will see. Just self-inductance, just keep it pending for some time. I will explain self-inductance. Mutual is basically between two coils. One coil is having current, another coil does not. So when I have a current, you should also have a current. So the other coil is influencing the other one. Okay. In both cases, the flux through a coil is proportional to the current I. Okay. So suppose this coil now, after some agreement, disagreement, some current is induced over here. Okay. The flux which is linked with this coil is proportional to the current I. Flux is always proportional to current I. Obviously, if the flux is constant, if this current is constant, there will be instantaneous current for few seconds, then there will be no current, because flux will be constant. If flux is constant, then there will be no induction. Okay, so this flux is actually one mistake I made. This flux is dependent on this current. Okay, flux is dependent on this current. Flux through the secondary dependent on flux through primary. Okay, this is called primary, this is called secondary. We will come to that. Don't worry. Okay, for n terms, flux linkage is n phi, and n phi equals to proportional to I. Okay, the constant of proportionality is called inductance. It depends only on the geometry of the coil and the intrinsic properties of the medium, just like capacitance. Okay, SI unit of inductance is Henry, and after Joseph Henry, the name of the scientist who involved in this is Joseph Henry. Okay, inductance is a scalar quantity. Its dimensions is ml square t to the power minus 2 a to the power minus 2. Very simple, m l square a to the power minus 2 t to the power minus 2. Now if you remove this proportionality sign, then you get a constant that is called inductance. Okay, now obviously if this is a primary, this is the secondary, then generally the mutual inductance is between these two coils. It only depends on the geometry and orientation of the coils. Okay, it does not depend on the current that is flowing in the circuit. Okay, now mutual inductance of two coaxial solenoid. To coaxial means what? So this diagram looks little scary. Okay, coaxial means you have one coil and you have another coil inside it. Now if you repeat this, then it is a coaxial coil. Okay, let me do one thing. Let me draw using two different colors. So suppose we have, this is the main coil. Okay, this is the main coil. Okay, and inside this coil we have, inside the same coil we have another little smaller coil which is matching the bigger coil turn by turn. Okay, so this is called coaxial coils. Coaxial means their axis is same, they have the same axis, then it is called coaxial coils. Okay, here the diagram is, this is the outer side was the bigger one and the inner side is a smaller one. Okay, so current, now here obviously we have two coils. One coil, say this coil say S1, the bigger coil say S1, the smaller coil say S2. Okay, now if current in S2 is I2, then you can write B2 equals to mu naught into I2. Flux linkage, okay, so I think they are saying that S1 is inner, S2 is outer. Okay, I just made it wrong. This will be S2, this will be S1. This is S1. Okay, so now this one S2 is the main driver. S2 is the main driver. It is driving the everything whatever is happening inside. I am the bigger brother. I will drive this car. Okay, whatever happening inside the car is my responsibility. So S2 is that person. He is the bigger brother. He is saying whatever happens inside is my responsibility. So I will drive the car. So suppose the current through this is I2. Okay, then what is the magnetic field that is produced inside? So magnetic field inside a solenoid is given by mu naught Ni. Okay, mu naught N2 I2. N2 is the number of turns per unit length for this one. Say N1 is number of turns for the other one. They can have separate number of turns. Okay, they can have same number of turns, but assume that they have separate number of turns. Okay, so B2 equals to mu naught N2 I2. Okay, this is the magnetic field due to the bigger brother, the outer coil. Okay, so what is the flux linkage with the inner part? Flux linkage with the inner part is given by, suppose this is the area of this coil. Okay, flux linkage with the inner coil will be given by magnetic field into area into number of turns. Okay, for one coil it is B into A, because there are n number of turns, so that you have to also multiply with n1. Okay, B is B2. Okay, B2 is mu naught N2 I2 into area. What is area here? Suppose the radius of this inner part is R1. Radius of this inner part is R1, then it will be Also you have to multiply with the length of this thing, because flux is not only per length, magnetic field is per length, unit number of turns per length, but total number of flux, it should be capital N1. Capital N1 is what? Capital N1 is the length of the coil into the number of turns per unit length, right? This is number of turns per unit length, this is number of total length, so total number of turns is N into L, so it will be N into N1 into L. L is common, into B into phi, B into area. Now what is B? B is mu naught N2I2. What is area? Area is the area of this inner portion. He has a radius R1, so pi R1 square. Okay, so this is the flux that is linked with the inner coil. Okay, this is the flux that is linked with the inner coil. Okay, now if the current which is induced in the inner coil is given by I1, if current which is induced in this coil is I1, then this must be proportional to the quantity mutual inductance of 1 due to 2 into I1. Okay, current in the inner part is I1, so you can compare it and you can find out what is the value of mutual inductance. Now, one very interesting point over here is that the mutual inductance, if this is the driver, if outside is driver, mutual inductance say M21. If inside one is the driver, then mutual inductance say is M12. When two coils are there, it does not matter who is driving. If there is an accident going to happen, it can happen with any one driver, right? So that is the same thing in physics also. So it says that mutual inductance of 1 due to 2 or of 2 due to 1, it is same value. Okay, mutual inductance M12 or M21 both are same, and that is given by mu r mu naught N1 N2 pi r square L. Basically you need to remember that mutual inductance is directly proportional to the N1 N2 R and L. Okay, now one very important point, it does not have anything else. That means it is actually only dependent on the geometry of the shape. I1, I2, it is independent of I1 and I2. How much current is flowing, how much rate of change of current, that is not dependent on mutual inductance. Mutual inductance only depends on geometry. Geometry means number of turns per unit length, the length of the coil. So it is the only thing that these things depend on. Okay, now obviously there are if both number of turns are same, you can find say that N1 is equal to N2, then you can say N square L. Okay, so that can be a slightly challenging, but yes, this is the general formula. Based on this formula, we have only seen that once that mutual inductance is proportional to length. Based on that, once question came. Okay, mutual inductance. Now when mutual inductance, we are talking about mutual inductance, there has to be some both coils have same mutual inductance. So if their configuration is fixed, these two coils have a fixed mutual inductance, and that is denoted by M. No matter who is driving, the current is flowing through I1, current is flowing through the inner coil and outer coil is getting induced, or current is flowing in the outer coil and inner coil is getting induced. So one of them will be driver, second one will be just induced current. Okay, it does not matter who is forcing it. Whoever force it, the mutual inductance between them will always be same. Okay, if you die, I will also die, right? So that is what you need to be careful about. So if the induced EMF due to current flowing in the second coil S2 into the 1 is given by epsilon is equal to minus M di2 by dt. So remember that mutual inductance is given by minus M di dt. Okay, mutual inductance is M di dt. That is a shortcut formula you need to remember. Varying current in one coil induces EMF in a neighboring coil. Magnitude depends on the rate of change of current and on mutual inductance M. Okay, it depends on rate of change of current and on M. Okay, two concentric coplanar coils, so they are actually center is same and the planes are same. Okay, current I2 in the large coil gives the field at the center B2 is equal to mu naught I2 by 2 pi R2, nearly uniform over the small coil. Flux through the small coil is given by this, and M is also depends on the separation of the coils and their relative orientation. So mutual inductance is not only dependent on their radius, length, etc. Okay, it also depends on how they are oriented. So suppose we have one coil like this, another coil is like this. Okay, their orientation also determines how much EMF will be generated. Okay, it also depends on the orientation. So so far what we are discussing here, they are concentric. Now instead of concentric we have one coil like this. Okay, I said another coil I want to have like this. Okay, they all have different configuration, or maybe one coil say like this, another coil say like this. So how they are oriented, their angle between these coils, that also changes their mutual inductance. Okay, it depends on the orientation as well, relative orientation as well. Next is self inductance. Self inductance is like suppose what is mutual inductance? You committed a crime and government is punishing you, or the system is punishing you. That is like mutual inductance. You committed a crime and system is punishing you. Now you committed a crime and you are thinking inside yourself, I have committed a crime. I should not do that. I stole a chocolate from my friend's bag. I should not have done that. Okay, or I should not have cheated my friend while I was playing Free Fire. So that is a self guilt, right? So that is what, no one is going to punish you for that, but that is a self guilt that is developed inside you. I should not have done that. So that self guilt is there in case of a single current carrying coil as well. We have a single current carrying coil. Okay, one single coil, assuming one coil only. Okay, and we have some arrangement to force some current through this. Suppose we have an arrangement through which current can be passed through this coil. Simple battery, simple coil. Okay, so we are basically trying to send current through this coil, and there is an EMF source, a current I is passing through this. Okay, now what will happen? So when the current is passing through this, okay, this will produce a magnetic field. In a current carrying coil, we know there will be a magnetic field produced inside the coil, right? Expression for that we have done in moving charges and magnetism chapter. So now when the current is passing through this coil, okay, suddenly it realizes, okay, I have a varying magnetic field linked with myself, which is produced by me only. Okay, so this coil is having that feeling that this me is talking to that me via this me, right? Those who know knows. So same thing happens with this coil as well. He thinks that whenever current is passing through it, immediately some magnetic field is generated, suppose say out of the page. Okay, and immediately that magnetic field is telling the coil, hey, I am here. Okay, so you should also produce a induced EMF inside you as well. So basically this coil is responsible for producing the magnetic field, which is in turn is inducing a current in the circuit. Understood? So this is the coil, he is producing a magnetic field, and that magnetic field is in turn producing a response in the same coil itself. That is what is called self-inductance. So I am the culprit, I am producing something, and then he is hitting me back with the same thing. That is called self-inductance. So the magnetic field produced by this coil is in return, as a return gift, it is producing a induced EMF in this coil as well. Now remember, one very important point is that according to Lenz law, the induced EMF should oppose its cause. Induced EMF should oppose its cause. So if the current in this loop is flowing like this, so this is the inner part and then it is going like this, okay, then the induced EMF will be produced exactly in the opposite direction. So induced EMF will be exactly in the opposite direction. Okay, this is induced EMF, induced current, okay, or induced EMF. So induced EMF will try to produce a current exactly in the opposite direction of the inductor. So as soon as you switch it on, there will be a change in flux, and that flux change will induce a current which will try to stop the current momentarily. Now if it is a DC source, it will stop after some time, okay, but if it is an AC source, it does something really interesting that we will see in our next chapter, alternating current, okay. But anyway, for now, assuming that as soon as there is a current is being produced, okay, that current is trying to stop the original current, and that there is a clash between them. So induced current always opposes the cause. Induced current always opposes the original current, that is Lenz's law, okay. So EMF is induced in a single isolated coil when the current through the coil changes, okay. It can be starting from 0 to suddenly switched on the circuit at that point of time, or it can be an AC current as well. Now flux linkage here is given by N phi equals to L into I. Same concept, there it was N phi equals to M into I, here it is N phi into L into I, okay. So here also magnetic flux is proportional to the current that is flowing, okay, and this is equals to M, sorry, not M, what I am doing, L into I, okay, and this flux in for one single coil it is L into I. If there are n number of turns, you need to multiply the number of turns as well. You have to multiply n number of turns as well, okay. Now induced EMF's value is given by L di dt. So if the di dt is 0, you will not get any induced EMF, okay. So for example, if you are using a DC circuit with inductor, this kind of configuration is called an inductor, okay, self inductor or inductor, okay, they are called inductor, they are also called inductor. It is same as capacitors. Now mutual inductance has also its uses. For example, transformer is the use of mutual inductance, but self inductance has more uses than mutual inductance. Mutual inductance has their fair share of applications, but designing ways, in terms of designing, mutual inductance applications are somewhat limited, but self inductance, they play a major role in many designs, okay, and many circuits as well. Okay, so circuits, all types of circuits require inductance to be present. Okay, so inductance is basically producing an EMF when the current is changing in the coil. So if di dt is 0, then you will not get any inductance. Okay, it always opposes any change, increase or decrease of current. If current tries to decrease, by the way, then induced EMF will increase. Okay, so that it try to balance the current. So if current is increasing, so the question where the answer that I gave you slightly confusing. So if in this case, suppose the current is increasing, if the current is increasing, then induced EMF in the opposite direction. If the current is decreasing, I have removed the key from the circuit. There was a key over here, that key I have removed it. Okay, initially the key was there, but what I have done, I have removed this key. Now in that case, what happened is that the current is decreasing. So as soon as current is decreasing, there will be an induced current which will flow in the same direction as the original current. Okay, so if current is decreasing, the induced EMF will try to oppose that as well. It will say no, stay as whatever you are. So inductance basically tries to maintain the same current. Okay, it does not allow increase or decrease of current through it. Basically that is the meaning of it. Okay, now for a solenoid, the inductance is given by mu naught mu r a into L. Okay, n square a into L. Okay, so a is the area, L is the length, n is number of turns per unit length. energy stored in an inductor. Energy stored in an inductor, it is same as energy stored in a capacitor. We have seen that in a capacitor the energy stored is half CV square. Okay, for inductor also can store energy same as capacitor. Okay, work must be done against the back EMF to build up the current. Rate of work is given by W by dt, which is given by epsilon. Okay, which is given by Li di by dt. Okay, so what is rate of work done? Rate of work done is actually the induced EMF into current. V is Vi. So rate of work done or energy power is actually given by voltage. Vodafone Idea is power. If you remember, I told you multiple times in our previous chapter. So here power is defined by rate of work done. Power is rate of work done, and that is given by EMF into I. Obviously we are only considering the modulus, we are not considering the sign over here. Okay, this is not from Faraday's law, so we do not need to consider any sign of EMF. So dW by dt is equal to E into I. Okay, so we are trying to find the work done. Our main target is to calculate the work done by this method. Okay, now what is induced EMF in a self-inductor? The induced EMF in a self-inductor is given by I into L into di dt. I am sorry, extremely sorry. I was just writing opposite. Current change, rate of change of current into self-inductance is the induced EMF. Okay, in a inductor. So inductor induced EMF depends on the inductance as well as the rate of change of current. So just put that value over here. So you get dW by dt equals to L into I into di dt. Right? L into I into di dt. Now obviously dt you cannot cancel it, but directly you cannot cancel it, but indirectly you can. So you can write dW equals to Li di. This derivation is important, especially for your midterm and pre-board exams. This derivation came once or twice in previous year papers as well, but most importantly it is important for your midterm and upcoming pre-board exams. Okay, so now you can write W, the total work done is integration Li di. Now L for a given combination is constant, so L will be coming out of the integration, so you get I di. What is this integration? I di is same as x dx, right? So it comes out to be x square by 2 plus c. That is the integration. But here we will use the limit 0 to I. So initially the current was 0. We are establishing a current to I. Okay, so that means how much work is done to establish the current 0 to I. So it will be a definite integration. So we do not have any constant over here. So it will be I square by 2 0 to I. Okay, now if you put the I, it will be I square by 2. If you put 0, it will be 0. So it will be Li square by 2. This is the derivation of work done. Now work done is stored as the energy. So energy will be half Li square. So this is the expression for work done and the energy stored in an inductor. Energy stored in an inductor is half Li square. Okay, so this is the work done. This is also the energy stored in the inductor. Okay. So kinetic energy is half mv square. L behaves like mass. Magnetic energy density. This is another important formula, by the way. Based on this, there was a question in the past. Magnetic energy density is B square by 2 mu. Okay. Electric energy density is half epsilon naught E square. Okay. In a capacitor. Okay, both are proportional to the square of the field. So if you see that magnetic energy is proportional to B square, electric energy is proportional to E square, the magnetic energy stored in this case is proportional to I square, right? That is one interesting thing. And if you compare the same formula with kinetic energy, this is potential energy stored in a inductor, half mv square. Okay, v is velocity here, I is current. Okay, the direct comparison says that L is actually like a mass. Okay, it is called, that's why it is called electric inertia. It is called electric inertia. What is that electric inertia? Inertia is what? Inertia is basically when you have a mass, okay, you apply some force on the mass is static at its place, right? It does not want to move from its place, right? So if you are standing in a bus suddenly starts, you fall in the backward side because your body wants to stay in the state of rest. Okay, similarly, if a moving car suddenly stops, you fall down in the forward direction because your body wants to stay in the state of motion. That is called inertia. Every object tries to retain its original state of motion, right? Whether it is a rest or motion. Okay, if it is a rest, it wants to retain its rest position. If it is motion, it wants to stay in its rest position. For example, the earth is rotating at a very high speed, 24 hours every day, okay, which is, for a size of earth, it is very high speed. Suddenly if it stops rotating, first of all of us will be moving in the opposite direction. We will fly away from the earth, most likely. Okay, so that could be a very worse, and everyone will start colliding with each other. Okay, so that is something very interesting fact you need to consider. Okay, so electrical inertia is same thing. It is trying to keep the current in a coil same as it was before. If it is changing, it is increasing, it will try to decrease it back. If it is decreasing, it will try to increase it back. So that property of induction, that's why it is called electrical inertia. It is try to prevent any change. Inertia means anything which tries to prevent any change, that is inertia. Okay, now last topic of the day, AC generator, but don't go anywhere, we have some a quiz as well. So AC generator, okay, converting mechanical energy into electrical energy. So the first if you remember, when we started our lecture of the day, we said that it is a baby. Okay, how do we know that what a baby gonna become in future? So this is the final ultimate conversion of the baby. Okay, when Faraday discovered his law, he jokingly said, this is just a newborn baby. Okay, we do not know about its future any. We have to wait for and see for its future. So this is the future. Okay, so when you were born, your parents never said that, okay, he will become an engineer or he will become a doctor. He said, we will see with time, right? So now once after you become something in life, then they will say, okay, my son is now a doctor, my son is a teacher. Okay, for example, my parents now say that my son is a teacher. Same, so that electromagnetic induction that started as a baby converted into an AC generator, right? That is the beautiful thing that runs our society. Entire society is dependent on this one very simple invention, and obviously we have modified it, we have done a lot of engineering around it, and nowadays modern AC generators are not like that what we are seeing here, but at its basic level, this is the same thing. Okay, obviously we have done engineering improvement from this design. This is a very basic design. If you use this kind of design, maybe you will not even produce any usable electricity out of it. But yes, the entire concept was built on this. This is a theory, then based on that, practical implementation. I told you, whenever someone gets a Nobel Prize, someone has to come up with a theory as well as a practical application. So this is one of the most practical application. Based on that, designers designed a lot of things. Okay, and I feel that whoever designed the AC generator should be given a Nobel Prize, because our entire society, our electricity, etc., is dependent on this as well. Okay, obviously it is not a single person job. It was done across generation, across a few 50-60 years, right? So first, what is the concept here? We have a north pole, we have a south pole. Okay, that means magnetic field is from north to south. Magnetic field is from north to south. So there is a magnetic field present over here. We have a rectangular loop present inside this. This is not carrying any current. In the previous chapter, we have seen that if we keep a current carrying loop inside the similar structure, it starts rotating. Okay, it starts rotating, it gets a torque, and based on that torque it starts rotating, right? And based on that rotation we design galvanometer, we design ammeter, voltmeter, etc. Also another very important discovery from that, that magnetic field, inside a magnetic field a current carrying coil rotates, is the generators, sorry, not generators, motors. Okay, many motors work on the principle whenever there is a current flowing in a circuit, that motor is rotating because of this magnetic field. One such example is our fan. Okay, fan is an example of a motor. Okay, electric motor. Okay, there are many types of motors. One is obviously the engine motor. Engine motor does not work in this way. Okay, engine motors have IC engine. Okay, so internal combustion engine. Modern day the electric motors, the electric designed vehicle, EV, okay, electrical vehicles, they work on this motor design. Okay, so they have a high power current passing through a circuit, that circuit rotates and that produces the required motion of the car. Okay, IC engines, the diesel engines, they work on the Carnot cycle principle that we have studied in our previous part, just for giving you a context. Now people thought, okay, current carrying wire in a magnetic field is rotating. Now what will happen, I take a normal wire without any current, and if I rotate it in a magnetic field, what will happen? So when the this is flat, magnetic flux or magnetic field lines passing through this is zero, because this is the plane, right? But when the plane is perpendicular, all the field lines are passing through this. Again, when it is flipping back, all the field lines are getting zero. So basically when it is rotating like this, what happens is that the field lines which are linked with this coil as it is rotating, okay, there will be field lines, flux linked with this coil will change. Field line, in other terms, the flux. What is flux? Magnetic field into area. So magnetic field, say given by B, the area of this, say A, then flux, maximum flux linked with this is B into A, minimum flux linked is 0. So based on the speed, how fast it is rotating, we will get a induced EMF. We will get a induced EMF. That induced EMF we can use in our day-to-day life. Okay, so coil or armature, this is called coil or armature. Okay, so armature is a technical term, we can normal way we can say coil. Okay, coil mounted on a rotor shaft. Rotor shaft means there is a shaft which is having some special design which can rotate, which can make this thing rotate in a electric field. Okay, and there are some techniques through which we can even collect the current as well. Okay, that is the engineering part, not physics part. Physics part is simple. We have a rotator. Okay, rotator, how does it rotate? By the way, if you are wondering, sir, how can we rotate it, we have a turbine system over here. We have a turbine system attached over here. Turbine means through which some water is flowing or some steam is going on or some air is going on. Okay, in case of windmills. So that's how it is rotating. Okay, so it is rotating by some external mechanical force. Okay, it is not any other electrical force is rotating it. Any other mechanical force is rotating it. Okay, mostly we use, either we use water, or old generation cases we use coal. You heat up the coal, then heated coal, actually what is the role of the coal power station? Coal power station, you cannot just simply burn the coal and get the energy. The coal is basically used to boil water. Okay, interesting, right? The boiling water now is being channeled toward a particular direction at high speed, and that high speed steam actually rotates the turbine, and that turbine in turn rotates in the magnetic field, and that produces required current that we are using in our homes. Okay, that is the coal power station. If it is a hydroelectric power station, okay, hydroelectric power station, it is produced by falling water. Water is stored inside a high place, okay, and then it is released with the continuous flow. So when the water is flowing through the turbine, it rotates the turbine fans, and then turbine fans rotate in the magnetic field, that produces the required magnetic field, required speed of the coil, and that produces required current. Okay, so these are the basic things. Okay, we can produce it by using windmills as well. Wind can rotate the fans of the windmill, and inside there is a engineering design which can rotate a coil inside the housing, and that coil rotation can produce magnetic field as well. Okay, now so the rotor shaft, through the rotor shaft, is rotated in a uniform field by external means. So this is the external means. It can be falling water, it can be steam, it can be air, okay, it can be something other than that as well. Okay, axis of rotation is perpendicular to the field, so it is rotating along this. So field is in this direction, axis of rotation is perpendicular to field, so that means it is rotating like this. It is not rotating in the parallel direction. Okay, if it is rotating in the parallel direction, flux change will be 0. You will not get any induced EMF. Okay, so rotation changes the flux through the coil, so an EMF is induced. Ends of the coil is connected to the external circuit through slip ring and carbon brushes. That is a design. Okay, converts mechanical energy into electrical energy. This is the AC generator's principle. Okay, a coil rotates in a fixed magnetic field, and due to rotation, flux linked with the coil changes, and that induces electric current. So if they ask you what is the principle of AC generator, you need to write in these lines. There is not one single line, you have to mention that a coil rotated in a magnetic field, fixed magnetic field, the flux linked with the coil changes, and thus it induces EMF or induces current in the coil. That current is collected, and that is the principle of AC generator. Okay, now let's see what happens if at some time, okay, the angle between the coil and the wire, say magnetic field is in this direction and the coil is at some direction theta. Okay, the armature. Okay, so if this is the angle theta, obviously it is related to the angular speed, how fast it is rotating. Okay, how fast it is rotating. Say this theta is after time t. If this theta is after time t, the theta will be omega t. You remember, suppose you have a circular motion. Okay, in a simple harmonic motion we have done that. Okay, it is rotating with angular speed. The theta is given by the angular speed is omega. Okay, then we also used in rotational motion as well, but in angular, this we also have used in simple harmonic motion. So theta equals to omega t. Okay, so what will be our flux linked? Normally flux linked is BA, but because the angle is changing, we also have to use cos theta component. Okay, cos theta, it is a time varying, theta is changing with time. B and A are constant here. B and A are constant, only theta is changing with time. So as it is rotating like this, the theta is changing, and because the theta is changing, the induced flux will also change. Flux changes means induced EMF will be produced. Okay, so this is the flux linked. We are assuming only one coil. If you are interested, suppose we have more than one coil. If we have more than one coil, then it will be NBA cos phi. Okay, NBA cos phi is the flux linked with this coil. Now what is the induced EMF according to we know that one more thing here, you have to write NBA cos omega t. Okay, NBA cos omega t. Omega t is the angle at some time t. Okay, so what is the induced EMF? Induced EMF is minus d phi b by dt. Okay, now you multiply it, you take it, NBA is constant, so NBA will be outside. Okay, d dt of cos theta or cos omega t. Okay, what is in differentiation of cos omega t? Cos theta is minus sin theta, so it will be minus minus plus NBA omega sin omega t. Sin cos AT is equal to A minus A sin AT, right? If you forget the differentiation, d dt of cos AT equals to A minus A sin AT, right? So the same thing we have used in this equation as well. So we get NBA omega sine omega t. And at time t is equal to 0, the EMF is given by NBA omega. So this is the maximum possible value of the induced EMF. This is the maximum possible value of the induced EMF. So you can write epsilon is equal to epsilon naught sine omega t. Epsilon is equal to epsilon naught sine omega t. So you will get this as the induced EMF, and in terms of frequency you can write this. Okay, this is the normal formula, epsilon naught sine omega t, and in terms of frequency you can write 2 pi nu into t. Okay, or 2 pi f into t. Omega is equal to given by 2 pi nu. Nu is frequency of the rotation. Okay, so here this epsilon naught is equal to NBA omega is the maximum value of the induced current, and as you can see the angle of theta changes with time. Okay, so as the theta changes, the induced EMF also changes. And one very important point is that this EMF is not constant with time. The EMF is not constant with time. As theta changes, the induced EMF is also changed. Okay, so induced EMF rises to the maximum value, it goes down to the negative value, then it goes back to this maximum value as well. Okay, so sine omega t can start from 0, it goes to 90, becomes 1, then 180 it becomes 0, then 270 it becomes -1, like that. Okay, so as the value of sine omega t is changing, the value of epsilon is also changing. So that means the epsilon is not fixed, it is varying with time. That's why it is called alternating current. This is called alternating current. So at some time it is positive, at some time it is negative. So it is switching between positive and negative, positive and negative. Okay, in fact our domestic power supply switches, this positive and negative switch happens 50 times every second. 50 times every second. Okay, so that's why this is called alternating current. You are not able to produce any direct current through this generator. There are ways to produce direct current, but mainly alternating current is produced using generators. That is easy and cheap to produce. Okay, now commercial generators, hydroelectric, water falling from a height, dams rotate the armature. Okay, thermal, steam from burning coal or other fuel drives the turbine. Nuclear fuel produces the heat instead of coal. Okay, so nuclear reactors, you might wonder how nuclear reactors work. It is same as thermal, only difference is that here the nuclear fuel produces the heat. Okay, there is in principle only difference is here you have a burner in thermal cases that burns the coal and the gas is emitted outside, and that coal is basically using to burn the water, sorry, not burn the water, boil the water, and that boiling water produces the required kinetic energy to the steam, and that steam moves and produces that steam actually gives rise to the motion of the turbine. Here in case of nuclear fuel, everything is same. Nuclear reaction produces heat, that is given to the water, water boils, it produces the required motion and the turbine rotates. Okay, modern generators produce power as high as 500 megawatt, enough to light 5 million. 5 million means 50 lakhs. 5 million means 50 lakhs. 50 lakhs 100 watt bulbs. EMF is maximum when the coil plane is parallel to the field where the flux changes fastest. Obviously, when the electric field is parallel, then it becomes fastest. Okay, because it comes from 0 to 90, right? 0 to 90 means maximum change in flux. Okay, now this is a formula sheet. Again, how can you get this formula sheet and this PDF? You have to click on the link in the description below and join our free Abhyas, free ACE KCET batch, not Abhyas, free ACE KCET batch. Once you join there, you will get the access to all the PDFs and all the important notes. There will be assignments as well. So what are you waiting for? Click on the free ACE KCET batch 20 2027 in the link given in the description. Join today, and as soon as you join, you have to register using your email ID and mobile number. And once you have done it once, then from next time onwards, you just need to log in via OTP received on your registered mobile number. So registered mobile number is important. Once you do so, you will be getting access to all these PDFs and all the lecture notes. Not only this one, all the previous lecture notes and previous works that we have done on our channel will be available there, and you will also get Ved AI support. So what are you waiting for? Go and join now immediately, right? So this is the formula sheet, whatever formulas that we have learned, the magnetic flux, then we have induced EMF, Faraday's law, okay, motional EMF, and the induced EMF in a rotating rod, okay, self-inductance, expression for self-inductance, mutual inductance, expression for mutual inductance, work done or energy stored in a magnetic field, okay, then the induced EMF in a generator, okay. Now it's time for us some MCQ practice. So now let us solve 10 MCQs one by one. Question number 1. A magnetic field of flux density 1 Weber per meter square acts normal to a 80 turn coil of area 0.01 meter square. If this coil is removed from the field in 0.2 seconds, the EMF induced in it is. So here you are thinking, sir, what is flux density? Flux density is actually nothing but magnetic field as well. Okay, flux density is magnetic field, which is flux per unit area. Okay, nothing new, but anyway, if you don't remember it, that is also fine, because flux density, if you see the unit is given here Weber per meter square, and if you see that area is given 0.01 meter square. So you can understand that from here to calculate flux, we anyway have to multiply those two values. Okay, we have to multiply those two values, that is 1 into 0.01. So 1 into 0.01, that is 10 to the power of -2 Weber. That is the flux. You don't need to write the unit, by the way, in the KCET. You only need to solve it. Next is the number of turn is given here 80 turns. Okay, and the coil is removed from the field in 0.2 seconds. So what is the induced EMF? Induced EMF is N d phi by dt, magnitude. Okay, here in KCET they will not ask you to negative or positive sign, but in PUC when you are answering, you have to use negative sign whenever applicable. So basically you have to find the magnitude. So N here is 80 and d phi is 10 to the power of -2, because when initially in the field, that is the value, finally when you take out from the field, the final flux would be 0. So when you are taking it completely out of the magnetic field, initial flux is 10 to the power of -2, final flux is 0, so it will be 10 to the power of -2 only, and the time given here is 0.2 second. Okay, 0.2 second means 80 into 10 to the power of -2 divided by 2 into 10 to the power of -1. 0.2 means 10 to the power of -1, so it will be 40, so it will be 4 and it will be 4. So induced EMF is 4 volts. Okay, if you consider the zeros, 1 minus 1 minus 2 will one of them will be reduced, then 0 minus 1 will be only 4. So correct answer for this is 4 volt. Okay, 4 volt is the correct answer. Next, so here as you can see, the solution is given 4 volt. Next, a circular coil is placed in a uniform magnetic field with its plane parallel to the field lines. Okay, the magnetic flux through the coil is, so circular coil is placed, its plane parallel to the magnetic field. So as I mentioned here, the angle is, this is the angle. Okay, this is the plane of the this is the area vector, this is the magnetic field vector. So the angle between them is 90 degrees. So here angle between them is 90 degrees. So phi equals to BA cos theta. Theta is 90 degrees. So this must be 0. So the flux linked with the coil is 0 over here. Okay, don't need to think too much about it. okay, it will be either maximum or minimum, it will be 0. Okay, plane parallel to B means the normal or area vector is perpendicular to B. Okay, so theta equals to 90 degrees, so phi is equal to BA cos 90 degrees. No field lines pass through the surface. This is the actual meaning of this question. Okay, no field lines passing through the surface. So in case you see a question similar to this and they say what is the following, which of the following statement is true, maximum number of field line pass through the surface, some field line pass through the surface, no field line pass through the surface, you have to answer no field line passing through the surface. Next, a metallic rod of length 1 meter held along east-west direction is allowed to fall freely. Given the horizontal component of Earth's magnetic field BH equals to 3 into 10 to the power of minus 5 Tesla and G equals to 10 to the power of 10 meter per second square, the EMF induced in the rod after t second, after t is equal to 2 seconds. So here we have horizontal magnetic field, okay, and we have a rod. Okay, horizontal magnetic field is from north to south, okay, from Earth's north pole to south pole, and you have a rod which you are allowing to fall in this, just a second. So you have horizontal magnetic field of Earth and you have a rod which you are allowing it to fall, okay, downward. So falling means you are just releasing it, and you are allowing it to fall freely. Okay, so how to solve this question? So magnetic field and the velocity, they are perpendicular, so it cannot be 0. Okay, here we are trying to find the induced EMF, not magnetic flux linked. It is a single rod. Okay, it is not any coil or loop. Okay, coil and loop, if the angle is 90 degrees, perhaps it could be 0, but here it is not like that. It is a rod, single rod. So what is the difference? Single rod can still produce EMF because it's called motional EMF. So motional EMF value is given by epsilon is equal to B into V into L. Now magnetic field is given, length of the rod is given. What about velocity or speed of the rod after 2 seconds? So here we will be using equation of motion. Because you are allowing the rod to fall freely under gravity, we can say that final velocity is equal to initial velocity plus gt. Okay, because it is falling downward, so it will be positive. Now initially it is starting from rest because you are just allowing it to fall. So when it is falling here, okay, so initially its speed is 0. Okay, so then after 2 seconds, whatever velocity it is gaining, that what we are trying to find out. So V equals to 10 into 2, that is 20 meter per second. Very easy question. Okay, only you need to understand the basic concept. BH is given and the length is given 1 meter. Okay, 3 into 10 to the power of minus 5. Velocity is 20, length is 1 meter. So it will be 6 into 10 to the power of minus 4 volt. 6 into 10 to the power of minus 4 volt. So correct answer is option D, 6 into 10 to the power of minus 4 volt. It can also be given in the exam. This same thing can be given as 600 microvolt. So you need to be careful about this as well. 600 microvolt or 0.6 millivolt. Okay, those answers can also be possible based on 10 to the power value. You need to check and then find the correct answer. Next, okay, this is the solution. So as I have solved, it will be 6 into 10 to the power of minus 4 volt. Next question. Two coils have a mutual inductance of 0.005 Henry. The current in the first coil changes as I is equal to Im sin omega t, where Im is the maximum current, 10 ampere, omega is 100 pi radian per second. The maximum value of the induced EMF in the second coil is. Okay, so mutual inductance is given. Mutual inductance is given. First coil changes I. Changing I is given in the first coil. Okay, and they are asking you what is the induced EMF in the second coil. Okay, so How to solve it? So we know that if you are considering the second coil, we can write the flux is actually given by the flux linked to the second coil is actually given by the mutual inductance into the current given in the first coil. Okay, sorry, current, what I'm saying, current in the second coil itself. Okay, so phi 2 is equal to Mi2. Now if we can find phi 2 which is linked with the first coil, then we can link them and find the value of phi 1. So let's not go into the detail. Let's find out. Induced EMF is given by M di dt, which is M Im cos omega t. Maximum when cos omega t is 1, so epsilon max is M into Im. Okay, so you just put the value. So this is the maximum voltage. Okay, I think they are asking about maximum voltage. Maximum EMF induced, sorry, my mistake, maximum EMF induced. That's what I am also thinking why it is like that. So maximum EMF induced is given by M di dt. Okay, you can ignore the sign, you can just take the magnitude of it, and then if you differentiate it, you will get that M value is given, I is given Im sin omega t. Okay, Im sin omega t. So sin omega t differentiation is omega cos omega t. Okay, maximum value is cos omega t equals to 1. So maximum EMF is given by M Im omega. Okay, so maximum EMF is M Im omega. What is M? M is 0.005. That means 5 into 10 to the power of minus 3. Im, what is Im? Im is given here as 10 ampere. It will be 10 ampere, and omega is given here as 100 pi. Radian per second is important. It should be radian per second. Any other unit, you need to convert it into radian per second. Okay, so how many zeros? 1, 2, 3 zeros are there, and 10 to the power minus 3. So these 3 zeros and 10 to the power of minus 3 will cancel. Our final answer will be 5 pi volt. Okay, it will be 5 pi volt. So answer is 5 pi volt. Okay, so correct answer here is 5 pi volt. Next, a solenoid of inductance 2 Henry carries a current of 1 ampere. The magnetic energy stored in the solenoid is, so what is the magnetic energy stored in the solenoid? It is given by half Li square. This is as simple as that. So half into L is 2 Henry and current is 1, so it will be 1 joules. Okay, so the energy stored in the coil is 1 joule only. Okay, not 5 joule, not 2 joules, 1 joule only. Easy, simple. Put in the formula and get the answer directly. Now again, if you want to download the PDF of this session and all the previous sessions as well, do not forget to join our free YouTube batch, which is given in the description section below, from where you can download the PDF. The batch name is Free Ace KCET 2027 batch. Okay, it not only KCET, it also covers your PU preparation as well, so don't worry. Okay, next is question number 6. The current in a coil changes from 2 ampere to 5 ampere in 0.3 second. The magnitude of the EMF induced in the coil is 1 volt. The self inductance of the coil is, so here the current is changing from 2 ampere to 5 ampere in 0.3 second. EMF induced is given and they are asking what is the self inductance. So we know that induced EMF is given by L di dt, again magnitude wise. Okay, now induced EMF is given here as 1 volt. Current is changing from 2 to 5. So 1 volt L 2 to 5 minus 2 divided by time given here 0.3 second. 0.3. Okay, so now just Simplify this and you will get the answer L into 3 by 0.3 or L by 0.1 or L equals to 0.1. Okay, so value of L is 0.1. Or 0.1. Now if you see the answer, all the options are given in millihenry. So don't be just see this answer and mark it. Many students will mark this as your correct answer because the answer that you have received is 0.1. No, here it is, we have not changed any unit, so this is must be in Henry. This is not millihenry. So if you want to convert it into millihenry, it will be 100 millihenry. So be very careful. Such questions are super common in KCET. Only student make mistakes is that they forget to change the unit. They solve it, they think millihenry is the answer and they blindly put 0.1 milli as the answer. It will be not 1, sorry, it will be 100 millihenry. Okay, 100 millihenry is the answer. So that is another trick that we have learned today, right? So when you are solving it, I was also initially a little bit confused what is the answer. I thought the direct answer will be given, but direct answer is not given. So 1.1 Henry. Okay, you are using everything in SI unit. So 0.1 Henry. So answer should be 100 millihenry. So be careful, do not fall for the trap. After solving the question, you found the correct answer and you mark it wrong because you forget to change the unit. So units are super important in when you are solving a question. 3 identical coils A, B and C are placed coaxially with their planes parallel. A and C carry equal currents in opposite senses. B is kept fixed while A and C are moved towards B with the same speed. B being initially equidistant from both, the induced current in B is. So let us understand. I don't understand the question first. Okay, 3 identical coils A, B, C are placed coaxially with their planes parallel. Okay, coaxial plane parallel. A and C carry equal currents in opposite senses. B is kept fixed while A and C are moved towards B with the same speed. Okay, so we have, so this is coil A, this is B, this is C. Okay, each, suppose this is carrying current in the clockwise direction, this is carrying current in the anti-clockwise direction. Okay, both are moving towards B with a constant speed. So what happens here, this will try to induce current in the anti-clockwise direction because this is the clockwise direction. So this will try to induce a current in the anti-clockwise direction, whereas this one, which is anti-clockwise, it will try to induce a current in the clockwise direction. Very simple. So clockwise current will try to induce anti-clockwise current. Anti-clockwise current will try to induce a clockwise current. And because of both currents forming in the same loop, the net current in the circuit will be 0. Net current in the circuit will be 0. Don't need to confuse it. Okay, do not need to use concept of mutual induction, etc. Just remember it is a basic induction question. Okay, clockwise current moving towards another circuit will try to induce anti-clockwise current, opposite current. Okay, and anti-clockwise current will try to induce a clockwise current, and they should cancel each other. Okay, so the current in this case will be 0. Okay, so A and B flux due to A and C are equal magnitude but opposite direction. That is also a point that you can think about. As A and C approach with the same speed, both fluxes increases at the same rate. Okay, net flux through B stays 0 throughout. So d phi by dt is 0. So no current is induced. So that is one explanation as well, that flux change is itself is 0. So no flux change means no induction at all. Or you can say that if you use the superposition principle, you consider one coil at a time. Okay, and then at the end you try to add them up, that also fine. So if you are moving one coil, it will produce a circular current, another coil produce anti-circular current. Okay, so they will cancel each other. That is also another explanation. Next, Lenz law is a direct consequence of which of the conservation principle? We know that it is a conservation of charge principle, right? Right? No. Lenz law is conservation of energy. Okay. Okay. Yes. Lenz law is conservation of energy. Okay. So the induced current aided the change. A magnet would accelerate infinitely with no work done, a perpetual motion machine. The induced current opposes the change, so external work must be done, which appears as joule heat. This is exactly the conservation of energy. So you cannot score out of out if you just drink some pills without doing hard work. There is no option but to do hard work or smart work, whatever you say. Work has to be done. Okay, work needs to be done for you to become successful in life. Right? Question number 9. A metallic rod of length 1 meter rotates at 50 revolution per second about one end in a plane perpendicular to uniform magnetic field of 1 Tesla. The EMF between the two ends of the rod is. So we have done this calculation that when a rod rotates in a magnetic field, the EMF produced between the two ends is given by half B omega L square. Okay, half B omega L square. So B is 1 Tesla, length is 1 meter. So everything is 1 except omega. So B is 1, L is also 1, but omega is not, so it will be half omega. So if you can find the value of omega, then it is done. Now what is omega? So omega is not 50, okay, it is 50 revolution per second. So you need to convert this into radian per second. How to convert revolution into radians? Revolution means 50 rotation. Revolution means 50 rotation in 1 second. 1 revolution is 1 rotation. 50 revolution means 50 rotation. So what is the meaning of 1 rotation? 1 rotation means pi by 2, pi by 2, pi by 2, pi by 2. So total angle is 2 pi. So 1 rotation is 2 pi radian angular displacement. Okay. So 1 rotation means 2 pi angular displacement. So basically omega revolution per second, if you want to convert it into radian per second, you just need to multiply 2 pi. Okay, you just need to multiply with 2 pi, you get 2 pi radian per second, that is 100 pi radian per second. So it becomes half into 100 pi or 50 pi. 50 pi volt. 50 pi volt. Now if you see the option, I don't think 50 pi is given in any of the options. So what you need to do, you need to multiply. How to multiply? What to multiply? 50 into, I told you, if nothing is given, take pi as 3. If nothing is given, take pi as 3, multiply, you will get 150 volt. Okay, the EMF induced here is 150 volt. Okay, now if you see that, which one should be the correct answer? Is it 50 or 100 or 157? Obviously the closest one, that is option C, 157. Now question would have been slightly tricky if 149 and 150 both are given as an option. So which one to choose? 150, 149, 157. Okay, these kind of answers are given. Then you need to check that the value that you have used here, the actual value of pi is 3.141. Okay, value of pi would be 3.141. So if you, and what you have used, you have only used 3. That means you have actually reduced a multiplier. So if you are reducing a multiplier, your actual answer should be more than this. Your actual answer should be more than this. So more value, more answer means, so you need to choose a value which is bigger than this value. So we have to choose 157, not 150 directly, even if it is given as an option. Okay, because we are actually using shortcut technique. So remember that when you are using shortcut technique, if you are reducing a value or increasing a value, suppose 2.9 was there, I am using, instead of 2.9, I use 3. So that means we are actually having a higher value than intended. So answer should be lower than that value. So based on question to question, you need to do the approximation and realize the value should be more than this value or less than this value based on your approximation for that question. Remember, in KCET, calculators are not allowed, so you need to solve it on your own, each and every question. Next, correct option 157 volts. So that's what I have done. Epsilon is equal to half B omega L square. Omega is 100 pi radian per second. So you need to convert it and you get 157 volt. Okay. So this is an NCERT example 6.6. This question is from your NCERT example. Okay. So if you are not able to solve this question, then you are in trouble. In an AC generator, the coil rotates with constant angular speed in an uniform field. The induced EMF is maximum at the instant when. So what is the formula for induced EMF? Induced EMF is NAB or NBA, National Basketball Academy, into omega into sine omega t. Okay, so this is the induced EMF value. So the maximum value will be when sine omega t's value is 1. Okay, so that means omega t is 90 degrees. That is the angle between the magnetic field and the plane. Angle between the magnetic field and the plane is 90 degrees. At this angle, induced EMF will be maximum. Okay, so flux, now here let us see the options. Flux through the coil is maximum, plane of the coil is perpendicular to the field, plane of the coil is parallel to the field, coil momentarily stops. So the maximum at the instant when the plane of the coil is perpendicular to the field. Okay, when the plane of the coil is perpendicular to the field, that is the moment where you will get the maximum amount of induced EMF. Okay, that is the very interesting question. Okay, so so plane of the let's see. Okay. So theta is equal to 90 degrees. So how can it be parallel? Just a second. Yes. Sorry, my mistake. So the area vector is perpendicular. Okay, area vector is perpendicular. So this actually represents the area vector. So area vector means the plane of the coil is parallel to the magnetic field. Okay, so area vector is, so if this is the area vector is perpendicular. Okay, magnetic field is in this direction. This is area vector. Magnetic field, the angle between them is 90 degrees. So at this instant, the epsilon is maximum. That means the plane of the coil is parallel. Plane of the coil is parallel to the magnetic field. Okay, so just again I made a mistake. You should also not make that mistake here. The plane of the coil is parallel to the field. That is very, very interesting. The plane of the coil is parallel to the field. Only then we will get maximum induced EMF. Okay, so this is a very tricky question. very conceptual question. So first of all, you need to realize that angle is 90 degree, and that 90 degree angle is actually the angle between the area vector excuse me, it is the angle between the area vector and the magnetic field, right? So that's what important. So if you take the angle 90 degree, that is not the angle of the plane. Plane is parallel to the magnetic field, but when the plane is parallel to the magnetic field, the area vector, which is normal to the plane, is making an angle 90 degree. Okay, area vector always makes an angle 90 degree with the plane. So if both of them are perpendicular, means definitely magnetic field is parallel to the plane. Okay, so that's what slightly confusing. Now let us look into the key takeaways. So what happens? Changing flux gives rise to EMF. Okay, not the field itself. So field, magnetic field, you have a coil, you have a very strong magnetic field, it will not produce a single induced EMF or single electron will move. Okay, as long as the magnetic field is fixed, induced EMF will be 0. So induced EMF will only happen when there is a change in flux. Induced EMF will only happen if there is a change in flux. Okay, so changing flux gives rise to EMF. Okay, not the field itself, but it is change. Matters epsilon is equal to minus n d phi by dt. Okay, nature resists change. So not only your physics teacher changed or your chemistry teacher changed in your college and you are thinking, oh, previous teacher was better, or someone else from the past was better. So don't think that. Nature also likes that. Nature resists changes. Okay, so if someone comes up with something new ideas, everyone try to stop him because nature does not like any changes. Lenz law, induced effects opposes their cause. Energy is conserved. Okay, energy is conserved. That is the main reason, that because energy has to be conserved, so that's why nature tries to oppose the change. Okay, inductance is electrical inertia. Okay, discussed it. So coil store energy. What is the electrical inertia means? Inertia means which tries to stop any changes. Okay, inertia is the tendency of anyone to stop any changes. If it is mass, it is called motional inertia. Okay, inertial mass, sometimes it is called inertial mass. Okay, so inertial mass and gravitational mass are same, but conceptually it is different. Okay, inertial mass is basically is also called inertia. So whenever we try to move ourselves, we have to put some extra effort, because our body is always in the current state. If it is moving, it wants to stay in moving. If it is at rest, it wants to stay at that rest position only. So inductance is equals to electrical inertia. Coil store energy, and what is the energy stored in a coil, which is given by half Li square, and oppose change in the current. Okay, so this is the end of today's session. I hope that you enjoyed a lot this session today. And again, once more, I am telling you that if you want to download this PDF and all the other PDFs that we are going to do in our channel, you must join the free YouTube batch that is given in the link of this description. Free ACE KCET 2027 batch. Once you join there, you will get access to all the lectures that we have done on our channel, as well as all the lectures that is going to come in our channel. The PDFs of those lectures also will be available there as well. Okay, so don't wait, join today, because further you are waiting, more you are falling behind than others, right? And also, if you think that this video is helpful for you, don't forget to give it a thumbs up and subscribe to our channel if you have not yet subscribed. Subscription is what drives us moving forward. So I hope that you have subscribed to our channel, right? So I will be back with more lectures live as well as in the recorded format. Till then, bye.